So let us recap what we have done so far in double integration. The last time we looked at double integration over rectangles. They are the simplest double integral that you can find. Why? Because all the limits of integration are numbers. They are all constants. And when the limits of integration are all constants, you can always switch the integrals. Okay, switch the integrals and switch the dx dy. In other words, the order of integration is not important. You can take either dx dy or dy dx. Just make sure you write the limits in the right places. And then we also said that when you take the double integral of a function over a region, you are finding the volume of the solid of that surface over the region, the solid formed by the surface over the region. Right? That's what we said. Good. Today we are looking at double integrals over general regions. General regions, by that I mean not rectangles. It could be a square, it could be a triangle, it could be over any surface. Okay? In this case, your limits are not going to be all constants, right? What you want, basically, for you to get an exact answer, the outer limits must be constants. So I'm going to show you how you integrate or find double integrals over general regions. In this case, the order of integration is very important. You cannot just switch like we did before over rectangles. Fubini's theorem, that was why the switch took place, does not hold in this case. Okay? How do we get the order of integration? You have to sketch the region. So get ready to start graphing regions using your calculator to graph these. Okay? But first, I need to explain the regions to you. You need to know when you put it as dx dy, when you put the order as dx dy, or when you put the order as dy dx, what does that mean? And it's very important that you choose wisely. Let me tell you. You can choose either dx dy or dy dx, but sometimes one is more difficult than the other. Okay? So you must choose wisely. But first, I want to explain to you what dx dy in the integral or dy dx mean. Let us first look at a vertically simple region. Okay, what is a vertically simple region? So let's draw. So this is y and this is x. So let me just draw, let me just do that. And this is y equals g2 of x, that's that curve. And let's say this one is y equals g1 of x, and it's bounded by these two lines. Okay? Defined by x equals a and x equals b. So this is the region that we are looking at. So suppose that the surface that you are looking at, the function lies above this region. Let us call it R. Okay? I want you to take a different color. It's vertically simple, and I want you to just put in a vertical strip like that. What is a vertically simple region? Right? Just imagine, think of Riemann sum. When we were doing Riemann sums, okay, we divided the region into strips, right? Vertical strips. Okay, so this region here, just imagine this region is divided into strips, okay? If you see this single strip that I have, if you keep on moving this strip throughout the region and the ends always lie on the curve, it is called a vertically simple. So if I move this strip, the bottom end is always going to lie on y equals g1 of x, and the top part is always going to lie on y equals g2 of x. This is called a vertically simple region. How do you integrate this? And this is the double integral. This is what you do. So if the surface is above that region, we say that the double integral of f of x y dA, we put dA because we're not sure of the order yet. Put r below here for me, please. Is equal to the integral of f of x y dy dx, means that this is vertically simple. And look at the limits. A to b would be the x limits, so that is why dx is on the outside. g1x to g2x are the limits for the y, and if you notice, they are the curves. For vertically simple, you move from bottom to up, bottom to up. These are the limits, the lower curve and the upper curve. So let me make a little note here so we can see. When you see dy dx, this means it is vertically simple that you have chosen. The next thing I want you to recognize, another thing, is that the limits on the outside, the x limits, must be constant. You cannot have variables there, okay? So these two limits are constants. And then finally, the y limits here, these are the curves. g1x is the curve at the bottom, g2x is the curve at the top. So we're going from bottom to top. Okay, so note the characteristics of vertically simple. Now let's look at horizontally simple now. So I'm sure you know horizontally simple now, you have to draw a horizontal strip. Okay, so y, oops. Y, x. So let's do that, let's do that. Let me see what I did here. Okay. So call this curve x equals f1 of x, of y. Call this one x equals f2 of y. And then it's bounded by two lines. This is C, and this is D, and this is your region R. Now take another color and then draw a horizontal strip. So what is a horizontally simple region? The same thing. If I take this horizontal strip and move it throughout the region, the left end will always lie on the curve x equals f1 of y. The right end will always lie on the curve x equals f2 of y. That is called horizontally simple. So let us look at the integral. So if we have this region and we are finding the double integral of this function which lies over it, f of x y dA, put r at the bottom here. So this is equal to the integral from c to d, the integral from f1x to f2x of the function dx dy. So a few things to notice again. dx dy here means horizontally simple. So note the order. Dx dy is horizontally simple. The outermost limits c to d are the y limits, and they must be constants. Okay? The y limits are constants. For horizontally simple, look at the limits of integration for the other integral. We go from f1 to f2. That means we go from left to right. Left lower, right upper. Do not get confused with this. Don't confuse vertically simple and horizontally simple. That's a common error. If you have chosen horizontally simple, you must go left to right. If you have chosen vertically simple, you must go bottom to up. Okay? That's very, very important. Okay. Now the first thing I want us to do before we start recognizing, drawing regions and recognizing whether they're horizontally simple or so on, I just want us to practice integrating. Okay? Doing the integrals over general regions. And maybe what I will do maybe for the first two questions is to draw the region so you can see what it looks like. Okay? It's not necessary, but maybe I will need to show you that. Let me first draw the region, okay? I'll draw it on the side there. So look at the limits. Now as you can see, this is dx dy, right? That's horizontally simple. Good? The y limit, so y goes from 0 to y equals 1. And x goes from y to x equals 1. These are the two limits we have. Outermost limits, y, 0 to 1. Innermost limits, x goes from y to 1. Now let's draw it. Let me see if you'd be able to shade the correct region. Okay, so I think we should draw this x equals y or y equals x line first. Okay, so you just draw it. Then draw x equals 1. So let's put 1 here. Now, look at this. Shade correctly. And then y equals 0 to y equals 1. So y equals 1 is here. Shade correctly. It's horizontally simple. So you go from left to right. X equals y to x equals 1. So this is the region that we are looking at. So in other words, this double integral represents the integral of x plus y over this triangle. Okay, so let's go back to the question and let's just integrate. I just want you to practice integrating. So let's do it. So put your 0 to 1. Put your square brackets. We are integrating with respect to x. So the integral of x with respect to x is x squared over 2 plus yx. And then put your x limit. So x goes from y to x equals 1 dy. Let's work this out. 0 to 1. So put 1 for x, so that's a half, plus y, minus, put y for x, y squared over 2, plus y squared dy. Now you need to work to simplify this before you integrate. When you simplify, you get a half plus y minus, what's that? 3 over 2 y cubed dy. Y squared, thank you. Integrate with respect to y, so that is just single variable calculus. That's a half y plus y squared over 2 minus, that's y cubed divided by 3, so that's a half, from 0 to 1. Substitute, you get a half plus a half minus a half, which is a half. Okay, let's do number 2. Again, let me show you what that region looks like. So look at dy dx. dy dx tells you that this is vertically simple. Okay? Alright, so let's let me take some blue here. So the limits, the innermost limits is the y limit. So you go from y equals 0 to y equals x squared. And the x limits, x goes from 0 to x equals 1. Okay, what does that region look like? So y equals x squared. Then we want y equals 0. So y equals 0 is the x-axis, right? So we're going from x-axis to y equals x squared. Then it's also bounded by x equals 0 and x equals 1. And so the region is this. Okay, so let's practice integrating this. So that is equal to, put 0 to 1, put your square brackets. We first integrating with respect to y. What is the integral of xy with respect to y? Anybody? Xy squared over 2. Y goes from 0 to y equals x squared dx. Substitute, put x squared for y squared. What do we have here? So x squared squared, that's x to the 4th times x. That's x to the 5th over 2. Well, y equals 0 is nothing. So I really did not need those square brackets. Dx. Any questions so far? Integrate. So that's x to the 6th over 12 from 0 to 1. And this leaves us with 1/12. Okay? So try this one. All I want you to do is to practice the integration. So just integrate this for me. You don't have to draw the region, just integrate it. So let's go over it. So that's 0 to 1. We're integrating in respect to y, so that's y plus y squared. Y equals x squared to y equals x dx. Substitute 0 to 1. Please use parentheses because signs are going to change and you have to be careful. So put y equals x, that's x plus x squared in parentheses, minus, put y equals x squared, that's x squared plus x to the 4th dx. If you do that like that, you will not run into problems. If you just put down the variables without any parentheses, you will forget about changing the sign. So this ends up just being x minus x to the 4th dx, which is equal to x squared over 2 minus x to the 5th over 5 from 0 to 1, which ends up being a half minus 1/5, which is equal to 3/10. Any questions on that? So you have to be able to do that before we start drawing regions and deciding whether we want them to be vertically or horizontally simple. Okay? So that's key. That's the first step. Any questions? Okay. Right. So we'll do this example first. We want to find a double integral over a general region. The first thing you need to remember to do is to sketch the region of integration. You have to sketch it, all right? After you have sketched it, then you need to decide whether or not the region is vertically or horizontally simple. Sometimes they are both, and so you can choose any. But sometimes one is easier than the other. So let's do number 1. Find the double integral of x squared plus y dA. It's over r. I forgot the r. Put an r underneath there. Where r is the region in the first quadrant between the parabolas y equals x squared and y equals 1 minus x squared. So draw these two parabolas. So we want y equals x squared, perfectly symmetrical. Oops, I was putting the other one. And then we want y equals 1 minus x squared. And the region we are looking at is the region in the first quadrant. Okay? So this is the region that we want. Okay? Now, I'll just put R because it's going to be a little messy here. So let me take out this thing here. And I'll just write R. Now, we want to decide whether this region, we want it to be vertically or horizontally simple. Take a horizontal strip and put it in there. You don't have to draw it. I will do it because I can erase it, okay? Let me just do it. If I take a horizontal strip and I put it in here and move it throughout this region, look at what's happening. It's flipping equations. So here, it's on the y-axis and then on the curve y equals x squared. But if I bring it up, look at what's going to happen. It's now lying on the other curve. This region is not horizontally simple. For you to make it horizontally simple, you have to split it in two. We don't want to do that, right? So let's take that out. And so it should be, let's see if it will be vertically simple. So put a vertical strip. And that works. Move it throughout the region. The bottom is always on the curve x squared. The top is always on the curve 1 minus x squared. So we want this to be vertically simple. And vertically simple means dy dx. Remember that, okay? So this means we need to find here. We need this point here. You with me?
Yes.
Okay, thank you for answering. To get this point, we need to solve these two equations. So put them equal to each other, because that is the point of intersection, right, of the two curves. So put x squared equals 1 minus x squared. 2x squared is 1. X squared is a half. So x, we only want the positive, 1 over square root 2. So this here, let me put it in blue, is 1 over square root 2. Okay, let's set up the integral and let's work it out. So we have the double integral. Let's put the function x squared plus y. We want it to be vertically simple, so put dy dx. Put the constants first, the x limits. Can anybody tell me what are the x limits? Good. 0 to 1 over square root 2. And now the y limits. It's vertically simple, so we look at the region, we go in bottom to top. Curve at the bottom to curve at the top. X squared to 1 minus x squared. Beautiful. So you have set it up. Note, please, if you set up the incorrect integral, everything is wrong. You have to get that right from the beginning, okay? Now let's integrate. So that is equal to the integral from 0 to 1 over square root 2. We integrate in with respect to y. So that's x squared y plus y squared over 2. From y equals x squared to y equals 1 minus x squared dx. Substitute 0 to 1 over square root 2. Okay, so put in one set of brackets, substitute 1 minus x squared here. So this becomes x squared times 1 minus x squared plus 1 minus x squared squared over 2. So that's only when I substituted 1 minus x squared. Minus, put x squared for y now, that is x to the 4th, plus x to the 4th over 2. Simplify that. Now I will allow you, you can put all of this into your calculator. Okay? Just put it into your calculator. And you will get 0 to 1 over square root 2, a half minus 2x to the 4th dx. Makes it really nice. Integrate. That's a half x minus 2 over 5 x to the 5. From 0 to 1 over square root 2. When you substitute, you get square root 2 over 5. I would also allow you to put this into your calculator and just write the answer down. Any questions?
Yes.
Let's go on to another example. Evaluate the double integral over r. I have no idea why I forgot the r's all the time. So put r underneath that double integral of 6x plus 2y squared dA, where r is the region bounded by the parabola x equals y squared and the straight line x plus y equals 2. So you draw the region. And if you don't know how these look, maybe you would have to do them on your, draw them on your calculator. But this is what they look like. So this is x equals y squared, and let's say something. So this is x plus y equals 2. Now look at this region. Decide. That's 0, of course. Do you want it to be horizontally or vertically simple? Decide. Horizontal. Beautiful. So let's draw a horizontal strip, because if we want it to be vertical, it will be a little more difficult, right? The vertical will work, you know, but it's just going to be more difficult. Okay? Good. So if it's horizontal, that means we want to know what this, we need our y limit. So we want to know what these, we need to solve these two equations. Okay, so we say horizontally simple. That's what we want. And horizontally simple is dx dy. That is why we need the y limit. So we take these two and solve. X equals y, put them equal to each other. So I'm going to substitute x equals 2 minus y into, well, it doesn't matter. I can substitute x equals y squared into the line. Alright, so we get, when I substitute, we get y squared plus y equals 2. Solve. So y squared plus y minus 2 is 0. Factor. Y plus 2, y minus 1, y equals minus 1 and 2. The other way around, isn't it? Yeah, thanks. So positive 1 and minus 2. So this is minus 2 and this is 1. All right? So let's set up our integral. Any questions so far? Okay, let's go. Let me go back to my black. So we're integrating, what are we integrating again? 6x plus 2y squared. Horizontally simple, so dx dy. Okay. Can somebody tell me what are the y limits? Very good. Negative 2 to 1. So that goes on the outside. Now the x limits. Remember, we are going left to right because it's horizontally simple. Which curve is on the left in the region? So you go y squared is at the bottom, and on the right would be the line 2 minus y. Very good. Wonderful. Okay. So now we're ready to integrate. Okay, so leave the outer one. We are integrating with respect to x. So you have 3x squared plus 2y squared x, and x goes from y squared to 2 minus y dy. So that's negative 2 to 1. Okay, let's make the substitutions. So here we're going to have 3 times 2 minus y all squared plus 2y squared times 2 minus y. That's the first substitution. Minus, now put y squared for x, That's 3y to the fourth plus 2y to the fourth dy. And again, you can put all of that into your calculator, and then you will get, when you simplify, you get 12 minus 12y plus 7y squared minus 2y cubed minus 5y to the fourth dy. Integrate 12y minus 6y squared plus 7 over 3y cubed minus a half y to the fourth minus y to the fifth from minus 2 to 1, and this gives us 99 over 2. Okay. All right. Any questions? Okay, I want us to do an actual application where, it's just find the volume. So let's do that. Find the volume of the solid under the surface z equals xy, so that's your function. And above the triangle, there's an a missing here. Above the triangle with vertices 1, 1, 4, 1, and 1, 2. You need to draw that triangle. Draw the triangle, then decide whether you want it to be vertically or horizontally simple. Okay? So let's draw it on the side here. So we want 1, 1, so that's 1, 1. We want 4, 1, 2, 3, 4. And then we want 1, 2, 2. So that's the region. That is your R. Do you want it to be vertically or horizontally simple? Does it matter? Does it matter? This is my question. It doesn't matter. They're both going to be the same. So you can take horizontal, you can take vertical. It doesn't matter. But what we should do before we do that, we need to find the equation of this line. You know that? We need to find this equation, this line equation. So let's work it out, okay? Let's find the slope. Well, we can see what the slope is. What's the slope? Negative 1/3, isn't it? Okay, slope is negative 1/3. And so now let's get the equation. So I'll use 1, 2 as a point. So y minus 2 is negative 1/3 times x minus 1. That's right. Okay, let's simplify. Y minus 2 is negative 1/3 x plus 1/3. Y equals negative 1/3 x plus 7 over 3. That's what I got. Okay. So this is actually y equals negative 1/3 x plus 7 over 3, right? If you do not like fractions, we can find what x is. Or, let's see. Let's multiply by 3. So 3y equals minus x plus 7. So x equals 7 minus 3y. So this curve is also, or x equals 7 minus 3y. So this is my point. This can either be vertically or horizontally simple. If you don't like the fractions, then I would choose horizontally simple. X equals 7 minus 3y.
So whichever equation's cleaner is the one we should go with.
Yeah. Well, it depends on you. I just don't like working with fractions. It's just a little, I don't know. It's just tedious. So I would take x equals 7 minus 3y and make it horizontally simple. Okay? But it depends on you. The integration will be the same. So let's make it horizontally simple. And it's dx dy. Okay? So let's do it. We have all our limits there already. So we find in the double integral of xy dx dy. Can somebody give me the y limits, please? 1 to 2. Horizontally simple, we are moving from left to right. What is on the left? 1, x equals 1. And what is on the right would be our line, 7 minus 3y. Okay? Okay, let's work this out. So this is equal to, leave the 1 to 2. We are integrating xy with respect to x. So that's x squared y over 2 from x equals 1 to x equals 7 minus 3y dy. Substitute 1 to 2. Put 7 minus 3y first. So that's x squared times 7. Sorry. Making an error here. We are substituting for, what are we substituting for? X, right? So that would be 7 minus 3y squared y over 2 minus, substitute for 1 now, y over 2 dy. Now when I simplify that, again, this is what you get. 1 to 2, I'm going to put a half outside, and inside you have 48y minus 42y squared plus 9y cubed. That's what you get when you simplify. Integrate, leave the half, integrate 24y squared minus 14y cubed plus 9 over 4y to the 4th, 1 to 2. And this leaves us with 31 over 8. Okay, so I thought I'd do that application. Right. Any questions? Okay, so I want you to try this one on your own. Now, I'm asking you don't have to evaluate it. Just set it up for me. Draw the region and set up the integral, okay? Because I want to make sure that you can set up these integrals. That's very important. Do not evaluate. Just set it up. And draw the region first. Just let me point out that this region can either be horizontally or vertically simple. So I want you, because you're only setting up, I want you to set up both versions. Do both horizontally and vertically simple. Do not evaluate, just set up, okay? Let's work it out here. Draw. y equals x squared, 0 to 1. So this is r, and I'm missing the r again here. So if you want it to be vertically simple, you want it to be dy dx. So the x limits are 0 to 1. The y limits will be from 0 to x squared, bottom to top. Any questions here? Horizontally simple now. You want it to be dx dy. So y goes from 0 to 1. Now, the x limits, you go from left to right. So what is on the left of that region is a curve, right? Y equals x squared. But what is x? Square root of y. So you go from square root of y. And what is on the right? 1. That's it. So don't mix it up. Left to right. Okay? Okay. Any questions? Now, just let me tell you, if you had to do it vertically simple and integrating this, you would have to use integration by substitution. In the horizontally simple one, if you had to integrate it, you would have had to use integration by parts. Okay? Depends on your preference. Let's move on. Reversing the order of integration. So sometimes you are given an integral to evaluate. But sometimes you cannot evaluate the integral using the particular order that you were given. And I'll show you an example in a little while, because there are some integrals that you cannot find. But you need to find that double integral. So what do? Reverse the order. Okay? So if the integral they gave you to find was dx dy and you cannot find it, just reverse the order to dy dx. And sometimes it's a lot simpler when you reverse the order. What do you need to do in order to reverse the order? First, sketch the region defined by the integral, and then reverse the order. So if it's vertically simple, then you now want it to be horizontally simple. Draw the strip. Okay, so let's do some examples here. Evaluate the following integrals by reversing the order of integration. Alright, so let's look at this integral, and what you should do is to write out the limits, because we need to draw the region, right? So the outermost limits are the y limits. So it says here that y goes from 0 to y equals 2. And the innermost limit says that x equals y over 2 to x equals 1. Now, x equals y over 2 is the same thing as y equals 2x, yeah? Alright, so don't get confused with that. Good. Now, if you notice, this was horizontally simple, right? And why must we change this? Because we cannot integrate this. Try integrating this thing with respect to x first. You can't. This is e to the x cubed. Cannot be integrated with respect to x. Alright? So you have no choice but to reverse the order. Okay, let's draw the region first of all. Let's draw the line first. So we're moving from y equals 2x. So draw y equals 2x. It's just a sketch, okay? Y equals 2x. And then x equals 1. So let's say this is x equals 1. And then the other limit, y equals 0. So y equals 0 is the x-axis to y equals 2. And I'm assuming that here is 2. So this is your region R. Any questions? Okay. So let's go. Let's change. So we now want to go to vertically simple. And we need dy dx. So if you need to draw your vertical strip so that you know what you're doing, do so. Sometimes it helps. Okay, let's change. And what's the integral? Y e to the x squared. X cubed? Thanks. Okay, you tell me, what are the x limits? 0 to 1. Vertically simple means we go from bottom to top. Alright? What's at the bottom? And the top? 2x. Done. Beautiful. Let's integrate. 0 to 1. Integrate this with respect to y is y squared e to the x cubed over 2 from y equals 0 to y equals 2x dx, which is 0 to 1. So put 2x for y. We have 4x squared over 2. So this is 2x squared e to the x cubed. And put 0 for y, that's 0. That's dx. Okay, how do we integrate this? Tell me. By what? Substitution. How do you know that? Very good. The derivative of x cubed is 3x squared, which is a multiple of the other function, right? So let's do it. So u equals x cubed, du equals 3x squared dx, divide by 3, du over 3 is x squared dx. Now this is an example where you change your limits. Remember we spoke about that early? So change from x limits to u limits. So x equals 0 implies that u equals 0. X equals 1 implies that u equals 1. Not much of a difference. So let's rewrite the integral. So this is equal to the integral from 0 to 1. Leave the 2 alone. E to the x cubed becomes e to the u. X squared dx becomes du over 3. So we're integrating 2/3 e to the u. When we integrate, we get 2/3 e to the u, the same thing, from 0 to 1. Substitute, you get 2/3 e minus 2/3. Done. So that's the first one. All right, let's do another one. All right, so notice that this is now vertically simple. Let's write down our limits because we need to draw the figure. So x goes from 1 to x equals 2. Y goes from 1 to y equals x squared. Let's draw. Y equals x squared. Okay, what do we have here? We need to go from x equals 1 to x equals 2. So let's say this is 1 here and this is 2. Okay? And then we need to go from, if you want, you can put a little dotted line. I don't know where this is going, that's why. I should have drawn it a little bigger, you know. And then for the y's, we need to go from y equals 1 to y equals x squared, bottom to top. Y equals 1 is here, and y equals x squared is there. So we have our region, R. Well, there's no R. Let me take that out and just put a... We want it now to be horizontally simple, so put a strip. Let me change the color. Sorry about that. Okie dokie, let's go, let's change. Change to horizontally simple. Okay, let's do this. So we have the double integral of x over y dx dy. So look at this. What are the y limits? 1 to what? To 4. Very good, because this is a 1. And then this here is 4. Because this is when x is 2, y is 4. Beautiful. 1 to 4. X limits left to right. What are they? X squared is on the left. And what is on the right? Are you sure? Okay, good. Thank you. Remember, when it's horizontally simple, you need the function. What is x? X equals what? Square root y. Beautiful. To x equals what? 2. So remember, left to right. Okay? Okay, let's do this. Let's integrate. So this is the integral from 1 to 4. Integrate x over y with respect to x. X squared over 2y from x equals square root y to x equals 2 dy. So this is equal to 1 to 4. Put 2 first for x. So that would be 4 over 2y, which ends up being 2 over y minus, put square root y for x, so the top is just going to be y over 2y, which is 1 over 2 dy. Integrate 2 natural log of y minus a half y from 1 to 4. And this leaves us with 2 natural log of 4 minus 3 halves. Please do not, please leave the answers exact like that. Don't put it as a decimal, please, okay? Just leave it alone. Okay. Number 3, let's do this again. Now this one we're not going to evaluate, we're only going to set up. Okay? Only set up. And as you can see, is this a vertically simple or horizontally simple? Vertically simple. Let's put down the limits. So x goes from minus 1 to x equals 3, y goes from x squared to 2x plus 3. Y equals 2x plus 3. Let's draw. Y equals x squared. Y equals 2x plus 3, something like that. Okay. And then x equals -1 to x equals 3. They're actually right here. This is -1. And this is 3. So as you can see, the region is clearly marked there. Okay, it's between the line and the curve. We want it now to be horizontally simple. Draw your strips. What do you notice? Move that strip through other region. What do you realize? It switches. Okay? Look at, we have a strip here and then put on the strip down here. You see what happens? Okay? So you need to split that region in two. So let's split it in two right here. Okay, so we have a little work to do here. We are making this horizontally simple. We want dx dy. Okay, let's start. Let's take the lower region first of all, the smaller one. So we have a double integral of, what is the function again? Just x? Dx dy. What are your x limits? No. Let me go again. Give me the, let me phrase it another way. Give me the outermost limit. So give me the y limits. 0 to what? To 1. This says 1, so you need to know what that is, right? Now, what are your x limits? That's a difficult one. Look at it closely. You are going from this side to that side, the left to the right. This is the curve y equals x squared, so you need to solve for x. Very good. Negative square root y to positive square root y. Fantastic. Okay, so we finished with that region. Let's go to the other region. So x dx dy. So look at the larger region, the one on the top. What are the y limits? Look at it. 1 to 9, because this is 3, right? So this ends up being 9. Now let's go again. This region, we're going for left to right. What is on the left of this upper region? The line. So you need to solve. Take that line and solve for x. What is it? Very good. Y minus 3 divided by 2. And then what about the curve? What's on the right? Square root y. Oh, you're rolling. Beautiful. Beautiful. So that's why I said we only setting this up, because it's a little challenging. Okay, this one, I only want you to set it up. Just set up the integral. Hold on. What did I do there? You need to change dA to dx dy. So change from horizontally simple to vertically simple. So try that one. Draw the curve and the line. So this is what it looks like, right? Oh, this is your, don't forget to put R underneath there. So you want this, x equals y squared, and you want something like this, right? Y equals x minus 2. This is your region in between there, good? Now, so this is horizontally simple, right? We want it to be vertically simple. What do you notice? Did you split it in two? Do you notice what is happening here? Look at where this strip is lying and look at where this strip is lying. You will need to split it in two down here. You with me? You have no choice but to do that. Okay? So, you will need to find these 2 points here. You need to find this. Okay? And to do that, you need to solve these two equations. Okay, so we need to know. All right, so let's just say we want to go vertically simple. So we want dy dx. So in other words, we want the x limits, right? So what are the x limits? So you need to substitute, you can solve for y if you want to, but I just solve for x right away. So I'm going to replace y with x minus 2. So x minus 2 all squared equals x. X squared minus 4x plus 4 equals x. X squared minus 5x plus 4 equals 0. X minus 4, x minus 1 equals 0. So x is 1 and 4. So this tells me that this here is 1 because that's a point of intersection of the line and the curve, and this here is 4. So this is a little challenging one, all right? Okay, I'm ready. We ready to set up? Okay, so double integral y dy dx. Let's look at the smaller region there. What are the x limits for this smaller region? 0 to 1. Good. And it's vertically simple, bottom to top. What's that? Bottom to top. Careful. Look at the smaller region, the curve. One curve is at the bottom, one curve is at the top. Negative square root x. You go in again. 2 square root x. Very good. Next region. Plus the double integral of y dy dx. Next region. What are the x limits? 1 to 4. Good. What are the y limits? Bottom to top. X minus 2 to square root x. Fantastic. Wow. Okay, so that was a difficult one. Let's do the last question. So this here is just a problem, but I want to show you how to handle these type of questions. Find the volume of the solid bounded by the cylinder y squared plus z squared equals 4 and the planes x equals 2y, x equals 0, and z equals 0 in the first octant. Now, you need to project this in the xy plane. Okay, so that you would, it's a double integral. so that you would know what your x and y limits are. This can be worked out using triple integration, which we will do later, but we're in double integrals now. Let's do that. The first thing, draw what you can in the xy plane. There are two things we can draw here. We can draw x equals 2y, we can draw x equals 0. So do that. And by the way, x equals 2y is the same thing as y equals x over 2. Alright? So when you draw that, you get that. And we are in the first octant, so we're in the first quadrant. Alright? X equals 0 is the y-axis, right? So this region is unbounded. Notice? It's open. We still need to find another line. How do we do that? We need to do some projection. The cylinder is bounded by z equals 0. Good? So take this z equals 0 and this y squared plus z squared equals 4 and solve them. Good? So we have y squared plus z squared equals 4, and z equals 0 implies that y squared equals 4. Which means that y equals 2. We are in the first quadrant. We do not need negative 2. So take y equals 2 and draw it. So this is your region R. Okay? Right. Now what are we integrating? Our function f of x, y, right? So we are integrating what z is. So take this y squared plus z squared equals 4 and solve for z. Z squared equals 4 minus y squared. So z is 4 minus y squared to the half. So this is what we are integrating. This is your f of x, y. This is the surface. Right. Okay, let's set up the integral. So we have the double integral of 4 minus y squared to the half. Let us decide. Do we want this to be horizontally or vertically simple? Now, be smart. You want it to be vertically? Okay, if you want it to be vertically, you want it to be dy. Don't write. You want it to be dy dx. Do you want to integrate this thing with respect to y? Look at that. This is a trigonometric substitution, you know. I don't want to do that. I don't know about you. I don't want to do that. So I don't want it to be vertically simple. Alright? I prefer, you can do it, you know, but you'll have a long thing to do there, I can tell you. It's going to be long and difficult. I like my dx dy. I'm sorry. So I am going to make it horizontally simple. So look at the integral before you decide, right? Okay, let's do this. What are the y limits? 0 to 2. What are the x limits? Left to right. 2y. Beautiful. Let's integrate. 0 to 2. Integrate with respect to x. So that's like a constant. So that's x times 4 minus y squared to the half. And x goes from 0 to x equals 2y dy. Substitute 0 to 2. We have 2y times 4 minus y squared to the half dy. Now, if you look at this, how do you integrate this? Any ideas? Substitution. Good. So we are going to let u equals 4 minus y squared du equals minus 2y dy. 2y dy is minus du. Change limits. Y equals 0 implies that u equals 4. Y equals 2 implies that u equals 0. Any questions so far? This becomes the integral. Now look at how I'm putting the limits. 4 to 0, because that is how we chose them, right? And this becomes a minus u to the half du. All right, let's integrate. This is u to the 3/2 minus 2/3 from 4 to 0. And when you substitute, you get 16 over 3. Any questions? Yes.
So when you changed it to minus u to the 1/2, where did the 2y go? I mean, oh, okay, that's your du. Okay.
You see?
Yeah.
Okay.
Thank you.
Yes?
What's the rule for your limits where you can switch limits and change your sign? What is that rule again?
If you have a negative, you can switch the limits and then change the sign. Just make it positive. Okay.